is curve sketching. So this page, the first one, just talks about how you would do curve sketching today versus, say, like when all of this calculus was invented. And there's all of this going around how about Newton invented calculus the last time there was a global pandemic, and there's still a big scam about whether Newton is really the one who invented calculus, so don't even get me started about that. But with that being said, if you actually look on a calculator, and let me find my calculator so that I can show you here. Let's say that you wanted the calculator to graph this example here. All right. So f of x equals x plus 4 over x plus 4. What do you think the calculator is going to give you? So, well, just visualize it, because hopefully you can see that this is 1, except when x is not equal to -4, because -4 would make the denominator equal to 0, right? So if I go ahead and I graph this, x plus 4 divided by x plus 4, and I go ahead and I graph this, see, the calculator won't even do that. Oh, I see. All right, you see that there is no indication to me on the calculator that x cannot equal -4. Now, I will say though that I think it is don't quote me on this, but I do know that I learned a way to get this to show this. I do remember that I learned a way to get the calculator to show this to you like a year ago, and I don't remember how it was done now, but that's okay, because you can see that if the calculator is not telling me this by default, there's a problem anyway, right? So an incorrect graph for this, an incorrect graph is sort of like the one you just saw in the calculator. Here is 1, and it looks like this. But the correct graph is going to look like this. It will have an open circle at -4 and look like this. All right, so do you see now what I mean by curve sketching or graph sketching? The it's the art of graphing these functions by hand so that you can see the important features that the calculator, the computer may have missed. Like the fact that there was not supposed to be a point at -4, 1. All right, and again, without knowing how to do this, your calculator is actually not, just not going to be able to handle this. So now, let's look at another example here. Oh, by the way, these are the 7 steps of curve sketching. So we'll go through an example of working through all of these 7 steps in a moment, but I want to look at page 205 and sketch a curve with the following properties. So for x is less than 1, we want f prime is greater than 0. So remember that f prime is greater than 0 means that f is actually increasing. F prime less than 0, f decreasing. And then if f is going from increasing to decreasing, then that means that there is a relative maximum. And if f is going from decreasing to increasing, that means that there is a relative minimum. And if f double prime of x is greater than 0, that means f is concave up, and if f double prime of x is less than 0, that means f is concave down. And so if f is going from concave up to concave down, so f is going from concave up or down to up, then that is a point of inflection. All right, so these are the things that you need to know. So here we go. So f prime is greater than 0. So f is increasing. So f is increasing. Then f prime greater than 0, f increasing. F prime less than 0, that means f is decreasing. And then you see the rest of these are f decreasing, f decreasing. So this means that the change here came between this interval and this interval. So that means that 0 is where f is going from increasing to decreasing, and that means that there would be a relative maximum at x equals 0. So try to remember this, that there is a relative maximum at x equals 0. All right, now f double prime greater than 0, that means concave up. So f is concave up. Then less than 0, concave down, down, and then back to greater than 0, so up, and then less than 0, back to down. So that means that at this point where there's a change from up to down, there's an inflection point. And then at this point where there's a change from down to up, there's an inflection point. And at this point where there is a change from up to down, there is an inflection point. So that means that there are inflection points. So inflection points at x equals -1, 6, and 8. All right, so let's go ahead and just draw this. So I know that from x is less than -1, f is increasing and concave up. So at some point, it reaches a relative maximum at x equals 0. So I'm just going to draw a relative maximum right now. And I need to be increasing and concave up. Now, remember that there's actually only 4 things that could happen. So it's going to be like this, like this, like this, or like this. All right. So this is the general shape for decreasing and concave up. This is increasing and concave up, increasing, concave down, and maybe I shouldn't use D for concave down and for decreasing, but I think that you know what I am getting at, hopefully. And then this is concave down, but decreasing. So decreasing and concave down. So down, down, there. Okay. So now up, up, down, down. Okay. So now I have increasing and concave up. So I want something that looks like this general shape. So I'll make it look like this. Then from negative, I said negative, I said -1. I said -1, and then I drew. I told you I from negative less than -1. So then from -1 to 0, I want increasing and concave down. So I want it to look like this. So I'm going to draw something that looks like this. And then from 0 to 6, I want decreasing and concave down. So decreasing concave down looks like this. So it looks, so here's, so I don't draw it too far again, here is, let me just highlight the interval. So less than -1, and then -1 to 0, and then we had 0 to 6, and then we had 6 to 8, and then we had from 8 and on. All right, so hopefully you see what I'm doing. I'm highlighting the intervals so that I don't overdraw the thing like I did the first time here. So from 0 to 6, I want decreasing and concave down, so something that looks like this. So it's going to just, it doesn't matter how far down as long as I end at 6. And then decreasing and concave up, so I want something that looks like this. So it's going to go like this. And then from 8 on, it will be decreasing and concave down, so it goes back to looking like this. And there we go. That's the general shape of the graph here. So we had concave up, then down, and then down, and then up, and then down, and then we had increasing, increasing, decreasing, decreasing, decreasing. All right, so I hope that you enjoyed this, because now it's time for an example of putting this all together, and it will be our last example here because it might take 5 hours. And here we go, page 206. Sketch the graph of the function using its domain, symmetry, intercepts, asymptotes, relative extrema, and any points of inflection. It really won't take as long as I'm making it seem, just 2 days. All right. So let's start by actually just going through the steps one by one. So we'll determine the domain of f, the numbers at which f is discontinuous, and the zeros of f, and the intervals on which f is positive or negative. So step 1. All right, so the domain. Well, the domain is already given here in the problem. So the domain is 0 to 2 pi. That's good, right? They're already giving it to us. Then I want to know if f is discontinuous anywhere, but f of x, if I look at what f of x is, cosine is continuous everywhere, and x is continuous everywhere. So then I know that, let's see, f of x equals 2 cosine x minus x is continuous everywhere. In particular, it's continuous everywhere on the interval 0 to 2 pi, although, again, it's continuous everywhere. And so now we want to know the zeros of f. So here we go. So that means that we want f of x equals 2 cosine of x minus x, and we're going to set this equal to 0. And, well, the fact of the matter is that are there any really good ways to figure out what this is? Well, honestly, there's not. All right, because like there's not an exact value that you will be able to find for this. So how would we solve equations like this in the past? Well, like, think about this. All right, you can make a guess for what you think that this is, right? Because let's just graph this really quickly. So 2 cosine of x minus x, and let's make sure it's in radians, right? Because mine was in degrees. Look at that. That would have been bad. So look here. Now, that we might want to go to zoom trig just so that we're a little bit clearer on this. But do you see that the 0 happens to be somewhere between 0 and pi over 2. All right, so, right, oh, by the way, if you do the zoom trig setting, this is pi over 2, pi, 3 pi over 2, and 2 pi by default. All right, so the 0 is somewhere between 0 and pi over 2. So by the graph, the 0 is between x equals 0 and x equals pi over 2, but pi over 2 is about 1.57. So why don't I just say, well, let's say that it's equal to 1, and we can use Newton's method to figure out what the exact 0 is. So use an initial guess of x equals, and let's just make that x0 equals 1, and Newton's method to find the exact 0. So, by the way, I forgot to mention that this problem here, well, you could actually use every single thing that we've talked about in this class up to now in the same example if you wanted to. All right, but for now, we're just going to start with Newton's method. So now x1 will be x0 minus f of x0 over f prime of x0. So f of x is 2 cosine of x minus x. F prime of x is a negative 2 sine of x minus 1. So let's use a calculator to do this. So what do we have here? So the function was 2 cosine of x minus x, and the derivative is minus 2 sine of x minus 1. And then here we go. So we have 0. All right, then we have that answer minus the function at that answer divided by the derivative at that answer. And so that will give us 2. All right, so let's say it's well, by the way, this seems a little bit, okay, yeah, that might be 2. Okay. Then we'll do that again, and we get 0.9951398,409. So x2 will be 0.9951398,409. And then we'll do this again, and x3 will be 1.030107307. And we'll do that again, and x4 will be 1.02986654. X5 will be 1.02986659, and x6 will be 1.02986659. So we see that with fairly good accuracy, we can see that the 0 is at x approximately 1.03 or so. All right, now what we want to do now is figure out the intervals on which f is positive or negative. So here we go. So if we have f of 1.03 is equal to 0, then all we need to do is figure out what is happening at values that are less than that and bigger than this. All right, so keep that in mind also. So let's just try this right here. So let's try f of 1. All right, f of 1. So f of 1 would be 0.08060461117. And let's try f of 2. F of 2 is going to be negative 2.8322936673. So hopefully you remember the intermediate value theorem and the change of sign theorem. This says that, right, that if a function goes from positive to negative, that the function has to have a 0 somewhere in that interval. So that means that on the interval from negative infinity to about 1.03, f is positive, and on the interval from 1.03 to infinity, f is negative. And right at 1.03, we have 1.030 as a point on the graph. All right, so far we actually know quite a bit about the graph, but now let's do step 2 here. So does anyone have any questions about Newton's method? I mean, I enjoy Newton's method, but I know that, it's probably not what you were maybe expecting here, but I personally really enjoy Newton's method. And Newton was a nice guy, except that I really think it's a scam whether or not he actually invented calculus or not. But that's a story for a different day. So now, step number 2. So, by the way, if in your time away from everything, if you're able to research on the internet and get an X-ray of Newton's bones, I'll give you 500 extra points, Howard. All right, so now let's see. Step 2, check whether f is even, odd, or neither. So how would you figure out this? So check whether f is even, odd, or neither. Oh, and by the way, Melissa, I saw that you were here earlier, so don't think that I didn't see you here either. So just don't think that you escaped yet. All right. So remember that a function is even if f of the opposite of x is equal to f of x, meaning that f has y-axis symmetry, right? And f is odd if f of the opposite of x equals the opposite of f of x. So that means f has symmetry with respect to the origin. All right, so now let's go ahead and figure out whether f is even, odd, or neither. All right, so f of x was the 2 cosine of x minus x. So does that equal f of the opposite of x? All right, so I'll just substitute the opposite of x in for x here. So we have 2 cosine of the opposite of x minus the opposite of x. So cosine of the opposite of x is cosine of x. That's an identity that you should remember for the rest of your life. All right, so here's an identity. The even and odd identities for sine and cosine. All right, so cosine of the opposite of x is cosine of x. So don't ever forget that. So we have 2 cosine of x plus x equals or does it equal 2 cosine of x minus x? So these are not the same, not the same. So f of x is not even. All right, so that means that there is no y-axis symmetry. So now let's try for the other part here. The f is odd. So does f of the opposite of x, which we just found over here, that will be, well, that ended up being, right, 2 cosine of x plus x. Did that equal the opposite with the negative outside of f of x? So 2 cosine of x minus x. That is a bright color. All right, I'm not using that one again. I told you I was trying out some new colors today, maybe. And then I'll distribute the negative here. So we have 2 cosine of x plus x equals the negative 2 cosine of x plus x. And these are not the same, right? One of them has a 2 cosine x, one has a negative 2 cosine of x. So these are not the same. So that means that f of x is not odd. All right, f of x is not odd, so there's no symmetry with respect to the origin. What a time to be alive, right? So now, step 3. All right, so step 3 was to find all asymptotes of the graph of f. So step 3, find all asymptotes. But the good news is that f has no asymptotes since it's continuous. Right? So that's the good news, is that that's the shortest step that we've had so far. Then step 4 is to find all critical numbers. So find find all critical numbers, and then find the intervals on which f prime is positive or negative, and then find the intervals on which the f is increasing or decreasing. All right, so let's use the first derivative to do this. So f of x was 2 cosine of x minus x. F prime of x was negative 2 sine of x minus 1. And we're going to set this equal to 0. So negative 2 sine of x is equal to 1. Then I'll divide by the negative 2. So sine of x is negative a half. So what does this mean then? It means that the, well, if I take the arc sine or the sine inverse on each side, so x is the sine inverse of negative a half, then those are the values that would give me the zeros or the critical numbers for the derivative, the zeros of the derivative are the critical numbers of the function. All right, so now I know that on 0 to 2 pi, the, where is it? I, I sort of, have lost it. Okay, so sine of 7 pi over 6 is negative a half, and sine of 11 pi over 6 is negative a half. So that means x equals 7 pi over 6 and 11 pi over 6 are the critical numbers. All right, so these are the numbers that are the possible relative maximum and minimum. All right, the possible relative maximum and minimum. All right, so let's go ahead and figure out which one is a relative maximum and which one is a relative minimum. So if you have any questions, again, please feel free to ask. So let's go ahead and graph the f prime of x. So we know that we have it from 0 to 2 pi. So here is the 7 pi over 6. So try to, as I said, just uh, try to remember that this isn't supposed to be that difficult, please. All right, because I don't want anyone to become angry. So this is pi over 2, pi, 3 pi over 2. All right, so yeah, so at 7 pi over 6, f prime of x is 0, and at 11 pi over 6, f prime of x is 0. So if you go ahead and you label these by 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So those are the zeros. And now you just need to figure out what is happening in between those zeros. So you can pick a bunch of numbers if you would like. So f prime of x was negative 2 sine of x minus 1. So here we go. And by the way, if you want to use a calculator, you can use a calculator. If you want to just go for it, you can go for it. It doesn't matter to me, because if you look here, you could have f prime of, say, pi is negative 2 sine of pi minus 1, and then you hopefully know that sine of pi is going to be 0, right? So you have negative 2 times 0 minus 1 is negative 1. So here is negative 1. So pi negative 1. And then at 3 pi over 2, f prime of 3 pi over 2 is going to be negative 2 sine of 3 pi over 2 minus 1. So sine of 3 pi over 2, what will that be? Well, oh boy, 3, yes. I'm telling you, this is the time of the day where I get hungry. But sine of 3 pi over 2 is negative 1. So negative 2 times negative 1 is 2 minus 1, that's 1. So here is 3 pi over 2, 1. And then we need, let's say, just to make sure that it's going negative again, like f prime of 2 pi. So negative 2 sine of 2 pi minus 1. So negative 2 times 0 minus 1 is negative 1. So 2 pi negative 1. And then even over here, if you want to know what is going on here, you could, but I think that at the same time, if you go ahead and you graph, oh boy, I I don't actually know where. Okay, yeah. So this was still negative 1, but if so, f prime of 0 will be negative 2 times 0 minus 1. So that will be well, yeah. So negative 2 times 0 minus 1, negative 1. But I don't know what I just did to the graph, honestly. I don't actually know. But you can see that here is the graph. So it goes down and then back up and then back down. So we actually don't care what this point is actually, at least not yet, all right? So now we see this is where the derivative is negative. This is where the derivative is negative, and this is where the derivative is positive. So luckily we're almost done here. All right, so this is where f prime of x is less than 0, f prime of x is less than 0, f prime of x is greater than 0. So that means that on this interval, f of x is decreasing, and here f of x is decreasing, and here f of x is increasing. All right, so now what do we have? We have f of x is decreasing on the interval from 0 to, what was that? That was 7 pi over 6 and 11 pi over 6 to 2 pi, and f of x is increasing on the interval from the 7 pi over 6 to 11 pi over 6. And then I also know that because the f of x is going from decreasing to increasing at 7 pi over 6, then that means that the f of x is going to increasing to, or did I say, yeah, increasing to decreasing at x equals, that would be 11 pi over 6. So that means that's a point where there is a relative maximum, and then the point where f of x is going from decreasing to increasing, that would be at x equals 7 pi over 6, and so there is a relative minimum. All right, so now that is the okay, what a time to be alive. All right, so that is the end of that example. So now let's just go ahead and look at the second derivative, and then we have to find the extremum, and then we will graph this real quickly and wrap it up. All right, so step 5. So the first derivative was negative 2 sine of x minus 1. Second derivative then will be negative 2 cosine of x. And what I'll do here is I will set this equal to 0 here. So divide by negative 2. So cosine of x is equal to 0. So then x is cosine inverse of 0, which is pi over 2, or 3 pi over 2 for the values n0 to 2 pi. So hopefully no one needs that. If you do, just say something in the chat room there. But then, all right, let's graph this. So this is a graph of f double prime of x. All right, so we have pi over 2, pi, 3 pi over 2, 2 pi. So it has zeros at pi over 2 and 3 pi over 2. So now we need f double prime of, say, well, 0. So it's negative 2 cosine of 0. So it's negative 2 times 1 is negative 2. Then f double prime of pi will be negative 2 cosine of pi. So hopefully you can see what is going on here, that at pi this is negative 2 times negative 1, 2. So pi 2. And then at f double prime of 2 pi, we have negative 2 cosine of 2 pi. This will be negative 2 times the 1. That will be negative 2 again. So this just looks like this. All right. So now here are the points where f double prime is less than 0 here's where f double prime of x is greater than 0. So f double prime of x less than 0 means that f of x is concave, well, concave, where is it? Oh, down. And then here we have f double prime of x is actually less than 0. So f of x is again concave down. And here f of double prime of x is greater than 0. So f of x is concave up. So this is on the interval from 0 to pi over 2, and this is on the interval from 3 pi over 2 to 2 pi, and this is on the interval from pi over 2 to 3 pi over 2. So then at x equal pi over 2, the f of x is going from concave down to up, so that means there's an inflection point. And then at x equals, where was it? 3 pi over 2, f of x is going from concave up to concave up to concave down. So that means there is an inflection point there as well. All right, so try to remember that. And now we need to figure out where is there a relative or absolute extremum. Well, all right, that's step 6. Locate the relative and absolute extremum. I really do hope that you're enjoying this, because after we locate these, we'll graph this and that will be it. I promise, all right? Except for Howard, you get an extra 2 days of this no sleep. All right, so now let's see. The relative extremum, these, remember, cannot occur at an end point. So now, here we go. So remember, the possible relative extremum were at the, oh, by the way, here, just so that you're all absolutely aware of this, I don't want to upset anyone at all, but just if you remember, 1, 2, 1, 2, 3, 4, 5. Okay. So here was x equals 7 pi over 6, and here was x equals 11 pi over 6. And so at 7 pi over 6, the graph was concave up. So that means that this is actually going to be, since the graph is concave up, it's going to be a relative minimum at this number and a relative maximum at this number, because it's concave down, because it was in the part where this is concave down. All right, so you could actually already verify that, because we said that, right? So this is the same thing that we just said. But now we really want to figure out which ones are the absolute extremums. So we have f of 0, f of 7 pi over 6, f of 11 pi over 6, f of 2 pi. So this is f. So f of 0, remember f of x was 2 cosine of x minus x. All right, so that will end up being 2. All right, so then you have f of 7 pi over 6. And by the way, I'm going to give you the decimals here only because of the fact that we're about to graph this, and it might make it easier for us to graph this if we have the decimals. All right, so this is about negative 5.3972422237, and f of 11 pi over 6 is negative 4.027535724, and f of 2 pi is about negative 4.2831 0.85307. All right, so I know that this point is a relative minimum, and this point is a relative maximum, and then the overall absolute maximum actually was at 0, 2. All right, so this is the absolute max, and then the overall minimum number, the lowest y value here was the negative 5.3972422237. So that is the absolute minimum. And now all you do is you graph this. All right, so just keep in mind that all we have to do now is graph these. So what do we know then? All right, just so that you're all clear on what do we know. All right, so here's what we know. We're on the interval from 0 to 2 pi, and we're trying to graph f of x is, what was it, 2 cosine of x minus x, and there's a point at 0, 2. There is a point at 7 pi over 6 negative 5.397. So here is a pi, then pi over 2, 3 pi over 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 2 pi. All right, so 7 pi over 6 and negative 5.39. So 1, 2, 3, 4, 5, negative 6. So 7 pi over 6, negative 5.39. Then 11 pi over 6. So 11 pi over 6, negative 4.02. So that would be about right here. And then f of 2 pi is negative 4.28. So a little bit like less than that. And then we also knew, all right, what else did we know looking back at the other steps so far? We knew that remember from the very beginning, we knew f of 1 was 0.08604617. So f of 1 is, all right, so yeah, so just try to remember this if you can, all right? So remember pi over 2 was about 1.57. All right, so if we want f of 1, then it's somewhere right about here. All right, f of 1. All right, so 1. And so that would be 0.08, and then 1.030. So, all right, so 1.030, that would be right here. A little bit less than pi over 3, which is about 1.04, and then pi over 6 was 0.523 or 524, just so that you know. And then we had f of 2. All right, so then, well, this is why I said that you might not want to graph these like by pies, just because this might get a little bit extreme for us, but that's okay. So about 2 negative 2.83. So that's about right here. Right, we had it 2 negative 2.83. And then did we have any other points that we knew about? I don't think that we did. If we did, I don't know about it. So So what does that mean? Well, that means we can graph this, and here we go. If you just kind of connect the points, it should be exactly what you expect it to be. So, by the way, there is another. Oh, we didn't graph the points of inflection. Where were those? I forgot those. Oh boy, yeah. At pi over 2, there's an inflection point. So f of pi over 2, so I didn't do that. So f of pi over 2 is negative 1.57. So f of pi over 2 is about negative 1.57. So here it is, negative 1.57. And then f of the other inflection point, 3 pi over 2. So f of the 3 pi over 2. What a mess, right? What a mess. All right. So then that's negative 4.71. So negative 4.71. So here it is. And now you can go ahead and graph this function. So what a time to be alive. So the graph of this function looks something like this. Well, and then it turns around because that's the inflection point, and then there's a minimum, and then another inflection point, and then a uh, a relative maximum, and then back down. So here we go. So just remember that this was the absolute maximum. Here is the absolute minimum. Here was a point of inflection. Here was a point of inflection. Here was the zero. And here was the relative maximum. And this was the endpoint over here of the interval. So other than that, you can see that the graph is increasing or decreasing or concave up or concave down in between. But this gave us a fairly good idea of what the graph looked like. So that's it. Like I would say, that's it for curve sketching.